recent work.
Hey, yeah, thank you very much for the invitation to attend the conference and enjoyed it very much. Now, Shor's algorithm, quantum error correction, has been around for 20 years. And people, experimentalists, have been making a lot of progress on this, but don't have a quantum computer for you yet. And you might ask, you know, after 20 years, is it really possible to build a quantum computer? This is hard, okay? And, you know, is it really going to happen? Okay, and, you know, clearly if for the field, it would be nice for it to happen. Now, I've been enjoying a lot of the computer science talks, and I like how they try to classify problems into various classes, okay? Generally with three-letter acronyms. So I wanted to talk about this in terms of a class. So I'm going to define EH as experimentally hard, okay? And to build a quantum computer, I'm going to say is experimentally crazy hard. Okay, that's how hard it is. So why is it crazy hard? First of all, we have to solve a bunch of scientific problems, that's just experimentally, okay? Second of all, we have to develop a lot of technology to get this to work. And that's happening with all the experimental systems. Ours is no different. So that's hard. And then the third part is that when we want to solve those technical problems, I don't ask for a lot of money and hire engineers to solve my problems. Because the quantum information is this is a new field. And we actually have to invent the technology ourselves. And I have to actually train students and postdocs to invent the technology so that we can make the advances. And that's the hard part. We're building this technology as we go along. And you know, given we've been talking about this, I wanted to write down a theorem here. ECH is not equal to MNP. And this is, MNP is maximum nature publications. Right? So we all know that's the goal of scientists now, is to get as many nature publications as you can. You know, for the students, they want to get the permanent job. And for the young faculty member, you want to get tenure and you want to go to invited talks, whatever. And the problem here is that doing crazy hard experiments where you have to invent technology is not the same mindset as publishing a lot of papers in Nature. Okay, that's one of our problems, okay. So now let's get serious, okay. Is it really possible to build a quantum computer? I want to talk about superconducting qubits and how in the last couple years a bunch of interesting things are happening where I now think it, you know, may be possible. It's surely crazy, it's surely hard, but if you look at what's happened, there's really a pathway to maybe do this. And you know, I'm convinced enough I kind of dropped, you know, this thing. Of course, we want to write nature publications, but I'm really starting to focus on this now. Okay, and what can we do to do that? So I want to talk about two main things. And one is surface code theory and error correction and architecture issues. And I think this will be nice for people to see how error correction will really work in kind of a physical system that we might be able to build. So this will be very concrete example. And I hope that will help you maybe think about how you might want to go about improving that and doing it real systems. And then I'll talk about superconducting qubits and some latest results where maybe we can put this all together. To kind of put this in context, one of the nice things about surface code theory is that the threshold for doing quantum error correction is not that bad. If we can make 25 nanosecond gates with this, the threshold is around 99%. So 100 times that is about 2.5 microseconds. And we're able to get coherence times 10 times or more above this, maybe even more if we do a little bit more work. So, you know, if you look at the raw numbers of gate times and coherence times, we're kind of doing better than the threshold. Of course, actually making accurate gates is another question, and I'm going to try to address that at the end. But you know, the numbers and the theory architecture looks kind of interesting, so we want to really explore that hard. So I'm going to talk about the surface code architecture, and it's actually not too hard. Basically everything is here, and I'll explain how it works. We have a square array of both data qubits, which are open, and measurement qubits, which are closed. And the measurement qubits and data qubits are just connected to each other via nearest neighbor, let's say C0 operations. So it's just this sea of qubits. And what's going to happen is the measurement qubits are going to measure the 4 data qubits around it. And there's 2 kinds of measurement qubits we'll call Z measure and X measure. And the circuit for doing that measurement is given down here. So the Z, the green ones, are a 4-bit just parity measurements where the classical outcome is just ZA, ZB, CZ, ZD. And this is, for example, the physical logical, the circuit diagram, where basically you have a ground state and then you do a bunch of C0s and you measure. And if these are all zeros, then ground will go to ground and you'll measure a 0 here. But if one of these are 1, this will flip this to the excited and you'll measure a 1. If 2 of them are 1, then you'll get 0 here. 3, you get high. 4, you get 0. Just the classical XR 4-bit parity. Okay? And then the same thing here in the orange-yellow is the same thing, but now instead of doing a bit parity, we do a phase parity. And this tells you the phase parity of the device. But it basically does the same thing. And what happens in the surface code cycle is you just start it off and you run this and you just repeatedly measure out of these measurement qubits the 4-bit parity and the 4-phase parity over and over again. So each one of these operations is maybe 20, 30 nanoseconds, and we would expect to repeat this every 200 nanoseconds or so. And every 200 nanoseconds we get let's say a plus or minus 1 out of all these measurements corresponding to the 4-bit phase and bit parity. Okay? So that's the basic operation. Now let's talk about how it works. And the first thing to realize here is that all of these measure X and Z 4 parities are going to commute with each other. So an X commuting to X or a Z commuting to Z is no problem. X computing with a Z far away, they're different qubits, they're going to commute. The only one you have to worry about is when they're right next door to each other, like drawn here. But notice that these are next door to each other. There's 2 qubits that they're measuring together. And it turns out that the commutation of X1 and X2 and commuted with Z1 and Z2, because they're 2 qubits, that commutation is 0. That's the essential thing you need to know. And then because of that, it means all of these commute. That means when you run this thing and you project it into an eigenstate by doing the measurement there, since they all commute, that means the next surface code cycle, you're going to get the same measure X and Z's. And the next one the same, the next one the same, because you're going to project it into a state of simultaneous eigenstates of all these bit and phase parities, okay? Now, it's going to stay the same if there are no errors. When you get an error, something's going to change. One of your measurements are going to change, okay? So let's just do an example. And let's say this data qubit changed. Well, that means the parity here is going to change, and the parity here is going to change. So this was maybe +1, and then when this thing flipped, it went to a -1, and this was -1. This thing flipped to +1. So when we run this, everything's going to stay the same in all the measurements, except here and here. And then we say, okay, with this error, one of these 4 changed. This error, one of these 4 changed. Well, this one had to change. And by looking at those pairs of errors in space, we now know that there is a data qubit error here. Okay, we run it some more. We see a pair of errors in Z here. It's one of these 3, one of these 4. Well, obviously, it's one in the center there. Okay, and that's how, when you have errors, you can measure, when you measure that, you can identify where the errors are. And you just do that and you identify the errors. If you want to correct the qubits, You can do that, or you can just store it in software. You can deal with it later if you want. One other thing that can happen is you could have a error in just one of these by itself. Say it was plus, 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 plus. Then at one point it was minus, and then you do it again, you'll get another error there. So you'll get plus, 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 minus, plus. These are pairs of error in time. And what that says is that you actually had an error in the measurement qubit, not in any of the data qubits. So it turns out that with these pairs in space and time, you can figure out what all your errors are. The only problem is when you get some errors and it's really dense. And then you have to back out, where the errors are here. And the problem is if this is very dense, you may not be able to back out the error uniquely. And that way, when you guess what the error is, you're going to guess wrong, and then you're going to make a logical error. Okay? And so that's where you have the real problems. And it turns out that making this bigger and bigger, the chance of you guessing wrong goes down, and then you get a fault-tolerant error correction. And I'll describe that in more detail in a few minutes. Now, I've been talking about how to correct errors. You want to know how can I encode information and make a logical qubit. So for this particular array, if you count the open circles, that's 41 data qubits. The closed circles are 40 measure qubits. You might suspect that you had an extra degree of freedom where you can store your logical qubit information. It turns out it's the case. In this case, you could define your X logical as X1, X2, X3, X4, X5, and ZL being 9, 10, 3, 11, 12. Okay? Now, it turns out that these logical operators commute with all the measures. Okay? So let's take X2, and or let's say this line here, and see this line here has 2. If you take this Z right here, you see there's 1 here and 1 here, and because there's a pair of this measurement commuting with X2 and X3, then it's the pair is going to commute, and you're going to be okay. Same thing here. The other thing to know that is if you take the commutation relationship, all these X operators will commute with each other except for this single pair here, so it's going to anti-commute, so that this looks like a qubit. Okay? Now, you might also ask, you say, well, you've defined in a certain way here, why don't I define my X logical by going from here to here, up to here, down here, here? You could do that, but the difference between this and this is just the X2, 6, 7, 8, and that's something we measure. We know that's plus or minus 1. So there's just a trivial constant between this and this, so it's the same operator. In fact, you can generalize this and saying anything starting from this side and ending up at this side is logically equivalent to this. So there's only 1 degree of freedom in this, and you store your qubit in that way. Okay, so that tells how to see the errors and make a logical qubit in the surface code. Let's now talk about logical error probabilities, because we want to do this with very low errors. So the way this is done in the computer programs is that we just take the surface code steps on a big array, and we go through and do the calculations where we put in a probability to P at each of these steps to do an error. So after the Hadamard, you have a P over 3 that's an X error, P over 3 that's a Y error, P over 3. Here, these are idle operations, again with an X, Y, or Z with the total error of P. These control Zs also have errors associated with all the 2-qubit poly errors. So you just run this, and then your errors pop up in the measurement, and then you use a minimum weight matching algorithm to say, okay, what was the real error? And then if you figured out what the real error was correctly, everything's fine. And if it didn't figure it out correctly, you then give yourself a logical X error. And you just run this Monte Carlo for a lot of cases, and you get curves here for the input error probability P per step versus the logical X error rate, let's say P sub L. And let's just take a 3 by 3 qubit array. You see that the error rate goes down as the square, this number squared down here. And if you get to a 5, it goes down, but now it's cubed. And bigger arrays makes this steeper and steeper. Okay? Now this curve automatically shows you what the threshold is for this system. It's right here. It's about 1%. And basically says as long as this probability P is below the threshold, you're getting smaller error rates as you make the dimension big. And if you're down here and you make the dimension big enough, then you can make your logical error rate go to 0. But of course, if you're above the threshold, that doesn't help you. So that defines the threshold. And if you go through and just kind of fit to this, you can say, yeah, this PL is about 5% times how much below threshold you are to this DE factor here. And that more or less tells you the logical threshold rate. Now, one of the nice things I like about the surface code, yes? It's just depolarizing. And you can put in more complicated things, but that's the standard model. That's what this is. Okay. No, we don't have any experimental data. That's too hard yet. But we're working on it. This is the data we want to get. Okay. So this is 5 by 5 qubits. And then you have the measurement qubits, so it's double that squared. And then DE is this plus 1 over 2. Okay. Now what I want to do is explain what's going on here. And one of the things I like about the surface code is I can write down what's going on here. I can derive for you using high school statistics. And it's not going to get it exactly right, but you're going to get the idea of what's going on here. Very simple math. Okay? So this is the idea. You have the logical qubit that goes across here, and there is an error, and we call this an error chain. We have errors here going across here from here to here. And when you look at this, you say, oh, okay, there was an error here. And since there was error here but not error here, I'm going to say the error there. So you naturally say, okay, let me identify this measurement with these particular errors. But if you look at this for a second, you see that also possible is for you to put an error here and an error here and an error here. And this particular error chain will give us this. So which one do you choose? They're both going to give this, what you measure. You won the one with the smallest probability. This had 2, this had 3, so you're naturally going to choose this, okay? But the problem is you're going to choose this, and every once in a while you're going to get this, and that's going to give you a logical error, okay? So the probability for this goes as p squared, this goes as p cubed. If you want to compute it in general, there's 8 of these steps here in the data qubits. So it's going to go as 8p, and then you can do the high school statistics, and you get a PL going like that. And, oh, what are you doing here? Ah. So here's the high school statistics formula, and you get basically this. You note that this is over by about a factor of 2, because there's other processes going on. It's a little bit more complicated. But you can see that this just very simple idea explains what's going on. This is nice because it really tells us how to get this thing to work properly. So with this formula, it's very nice. You can then say, if I'm below the threshold and I want a logical error rate of, say, 10 to the minus 18 to do some factoring algorithm, it says how many qubits I want. I need a dimension of 30 or so, and that's a few thousand qubits. Okay, so you need 3,000 physical qubits per logical qubit. And you need a lot of qubits no matter how you encode it, and you know, this just is a very simple way to know what's going on. And of course, if we go down here, right now we're targeting at 1/10. We might be able to get 100. In that case, instead of a few thousand, maybe I have to make 800 qubits. So less error, I just have to make it smaller. But, you know, not 5, I still have to do 800. Okay, if I want this, you know, tiny logical error. Okay? Now, so far I've been talking about how to take qubits and stabilize them, make no errors for a logical qubit, or for one logical qubit. but you want to say, well, how do I do operations? And this is what's really neat about the surface code, is once you make this big array, you maybe make one logical qubit, you maybe make it a little bit bigger, and then that basic computational structure, you can now do your logical qubits by just turning off some of your controls, okay? So the first thing you want to do is if you have a square array and you have one logical qubit, that's not very useful. So what you do is you make logical qubits by having interior holes in your surface code array. And for example, if you have two interior holes, one here and one here, you can define your operators this way and this way with Z and X, and they anti-commute and do all the nice things that I showed earlier, okay? Now, when you do it this way, let's say I want to initialize this qubit, the Z, in the Z basis. What I do is I have the surface code turning on, and I know what Z1, Z2, Z3, Z4 is. I measure it. And then what I do is in the next step, I just turn that off. And it turns out that when it's off, it just, this is whatever it was before I turned it on. I then go ahead and do my surface code calculation, and then at the end, I just turn this on, and whatever I got in Z1, Z2, Z3, Z4, that measurement is the final value. So by just simply turning this on and off, you can initialize a measurement. What's really nice with this is when you have pairs of these qubits, you can then do a C0 operation simply by moving this hole and braiding it around one of the other holes. And this braid operation, how do we move it? Well, what we do is we turn off these guys down here as if we were initializing it, and then we turn these on here as we're measuring it, but we never completely close it all the way. And since you know how you're turning it on and off here, you can then move that hole around. And you move the hole around, and turns out you get a C0. You can also do single qubit gates, like X and Z, Hadamard's, 90-degree rotations. These are Clifford gates, are pretty straightforward, not as easy as this, but not hard to do. And then, of course, to do the T gate, which is a 45-degree rotation, you need to create that special magic state and distill it in the normal way. One of the nice things about the surface code is the actual distillation process to do this is actually quite efficient. It's not so bad. I mean, this is all the resources. Most of the resources are in this gate, but it's not that crazy to do. It's not too hard. Okay, how much time do I have? Good. Okay, I forgot to turn this on. Okay, so what I'm going to do next is I'm going to talk about let me turn on my clock. I'm going to talk next about superconducting resonators and qubits, and talk about how far we're coming with that, and can we make gates good enough to do this. I like to think of these superconducting qubits as just electrical resonators, nonlinear resonators for a qubit. And let's just take an LC oscillator, a linear oscillator to start with. And this is a coplanar waveguide, so this is ground everywhere. There's a wire in here. But this can be readily mapped into an inductor capacitor resonator. And you can write down the Hamiltonian of the system and the commutation relations. It's just a harmonic oscillator. So in the end, you're going to have an energy, U of phi, that's quadratic. And then you're going to have energy levels in here that are spaced by h bar omega of the resonator. And they're going to be a 0, 1, 2, 3, but they're going to be equally spaced because it's a harmonic oscillator. And these have wave functions of, say, current flowing through here that kind of has the standard harmonic oscillator where current is flowing both to the right and to the left at the same time, as you expect for a quantum system. Now, this is a nice quantum system, and we can use it, but it's not useful for a qubit because these energy levels are all spaced equally. So if I put in a microwave excitation to, say, do a 0 to 1 transition, I'm also doing a 1 to 2 and 2 to 3 transition. So the occupation is going to wander through all these states. And you can't make a qubit out of that. So the magic here is that nature has given us a very wonderful element called the Josephson junction, which has a nonlinear inductance even with 1 photon of excitation in this LC resonator, okay? Having a nonlinear inductance is not a problem. You take any coil of copper wire and you put enough power into it, just before it smokes, it's going to go nonlinear. But it's high power. What's amazing here is this is nonlinear at 1 photon of energy, okay? And you work out the physics, it's also very low loss, just like superconductors are. So a Josephson junction this is just 2 aluminum metals separated by a natural barrier of aluminum oxide. It's made with E-beam evaporation and just bleeding in oxygen, very simple. This is thin enough so electrons can travel through here. And this forms a nonlinear Josephson inductance, okay? And you take the Josephson relation, I goes as sine phase. This phase is like a dimensionless flux. I is proportional sine of flux. If it was I proportional flux, it would be linear. The sine makes it nonlinear. And we actually integrate that to get the potential. You have a cosine potential. And that's the nonlinear cosine potential with the capacitor forms these wave functions. You see in green here, as I have the parabola, this cosine causes it to weaken a little bit. So you just quantize the system. These are very close to harmonic oscillator states. The important thing here is that the energy difference between here and here is different than the energy difference here and here. So now if I put in a long microwave pulse that's resonant with these two states, it's an off resonance with this state, and it'll stay within the ground excited manifold and stay within 2 states and act like a qubit. And of course, to put that in properly, you have to do control pulses and shape, etc., to make it fast, but that works. Okay, so just a nonlinear LC resonator. Now, we want to make long coherence time qubits. And in the last couple years, there have been some really neat advances into making what are called transmons, putting into a 3D geometry. This is done by the Yale group, and basically almost every other group in our group is now making these. Okay, and it's because we have long T1s and T2s around 60 microseconds. So you can do a lot of neat physics. These devices take advantage that intrinsically the junction is very low loss. And then what they do is they take a junction and put these paddles here that form the junction capacitance across the junction, and put this in a cavity. It's an aluminum box here. And the good capacitor here, most of the capacitance is just from air or from vacuum, which is low loss. And the fact that it's enclosed in a cavity means that this energy here won't radiate out. And because of that, they've made very good devices, and people are trying to figure out how to scale this up and do this. Now, what we've done is I've looked at this, and people, I think, may be able to do something with it, but I kind of dislike the fact that this is big, and also the fact that you're putting this inside of a cavity here to reduce the radiation. You're kind of what I call neutrinoizing the qubit. You're decoupling it from the rest of the world, which you have long T1s, T2s, but then you're also making it hard to couple to the rest of the world. So if I want to couple this to another qubit out here, I have to break this and do complicated things. And people are doing it, and it seems to be working okay. But what I want to do is I want to build quantum integrated circuits where I can have really flexible interconnectivity and design it so that this is all built into it. So to do this, basic idea here is we can put a junction connected to a big ground plane, and then we just capacitively couple between different junctions or readout or whatever, and then we have a multiple connected geometry where things work well. You have to do lots of materials research to get this to work, which we love. And with doing things right, we can get a coherence time that's very close to the 3D transmons with a lot of work to figure out how to get this all working. And also we have the theory for entangling gates, control Z between 2 qubits. That's very fast, very high intrinsic fidelity. So this is kind of what we're working on, and I'll show you data how we think we can get this to work pretty well. Okay. That's theory. Putting in all the, that's intrinsic, no T1, T2. But the basic operation to do that does not screw it up, we believe. We have to test that. So here's the Xmon design. What we do is down in this loop here, we have two Josephson junctions, and we bring in a DC current here that puts flux through this line, and that effectively changes the critical current, and it changes the frequency of the what we call the Xmon. And then in these lines here, this is ground plane, everything here, we have a capacitance from here to here, and that forms the nonlinear LC capacitance of the transmon. And then out here we have a capacitor here, this line here, which is a bus. And we have a capacitance, weaker capacitance here to here, which goes to a 50 ohm microwave line that can drive this, make ground to excited transitions. And then we have another stronger coupling here to our readout resonator. Okay? So we can have frequency Z, microwaves XY, bus coupling, readout, all in this simple structure. Just note here, this is really different than the standard transmon design. We've broken a bunch of design rules. The transmon is now outside of the resonator, direct microwave line, not through the resonator, this single-ended galvanically coupled, direct ground connection. All these things were thought to be death to transmons, but we didn't think so, and we got it to work. And because of this, we think there are a lot of advantages to this design. Excuse me? That's one qubit, and now we have two. And then we just connect this qubit through a resonator bus to this qubit. Here's the readout resonators to a microwave line. So you can add, and I hope you can see with these two here, we might be able to scale up more. And it's not too hard, in fact, to put more qubits on here. Well, that's still something, you know, we're working on. So we started this about a year and a half ago, not so great performance. And then we went to the Xmon and got a little bit better and simplified our materials and got near 10. And then did various things with molecular beam epitaxy aluminum. And just really figuring out what's going on, we got up to about 40 microseconds for our best device. We expect we can do better, and we're working on that right now. And for this whole year, our yield was 26 per 26 devices, and we can hit our qubit frequency to 100 megahertz. So we think we can scale this up. It really looks like we know how to make these devices. Of course, we've been doing this for many years. So now let me talk a little bit about readout. And again, this is following what was been pioneered by Yale and, say, the Berkeley group, a bunch of other groups. And what you do to read out is you take your Xmon qubit and you couple that to a resonator, and then you couple that to a transmission line coming out here and being measured. So we generate a microwave pulse here at a fixed frequency. This interacts with the resonator and the qubit, and what happens is whether the qubit is in the 0 or 1 state will change the effective resonant frequency of this resonator. So when you bring that through, whether you're in the 0 or 1 state, will give you a small phase shift here. You then amplify that with a quantum limited parametric amplifier, which is a whole research program in its own. Again, this is single-ended grounded. It's much better microwaves. Then we go to some low temperature amplifiers, and we bring in a mixer and an A to D converter to figure out what the phase is. And we just measure the phase of this and to know whether it's in the 0 or 1 state. So this is just the schematic of that. This is the real part of this signal and the imaginary part. If we're in the ground state and we do this 100 times or so, it's basically a Gaussian centered at this particular phase. Here's the 0, 0, so that particular phase right there. And if we put this in the 1 state, we then get most of it sitting down here and the 1 state. So we can easily distinguish between here and here. This is many widths of these distribution functions. You can also look at this dispersed signal just versus time, just continuously measure it. Then what we do here is this is where we turned it on. If you're in the ground state, you see it takes a while for this amplitude to build up, but then we're basically oscillating with some noise here. If you're in the 1 state, you're down here oscillating with some noise. Again, this is super discriminated from here to here over a fraction of a microsecond. Now the interesting thing here is doing a continuous is that you see very clearly a quantum jump phenomenon where you're in the one state and then every once in a while it jumps suddenly to the zero state. And this has been seen by a variety of systems, and you see that it's very clean here, very well separated jumps. You can do that. And when you look at this, you see this is so well separated, you have basically perfect intrinsic fidelity of the measurement system itself with these kind of time constants. The only errors that are coming here or between here is that this is jumping to this, or this is jumping to that. They're basically T1 errors. So the measurement fidelity is basically your measurement time over T1, about errors are about 5% or so, depending on how we do it. And you can kind of look at that a little bit more carefully. You just do an integration time and look at the signal-to-noise ratios as these two Gaussian peaks spread apart as you integrate longer and longer. And you see that at about 500 nanoseconds, 300 from here, maybe get error rate 5%. Yes, there's a question? Sure. Yeah. Yeah, the reds are covering up all the blues.
So they're much less.
There's a lot of blues here, and a few reds. The reds are decaying. There's lots and lots of points here, and these are mostly reds. It's just that the reds are overplotting the blue. This is mostly blue. Yeah, that's confusing. Thank you. Okay.
So this is not the system where you got like 40 microseconds time then?
This is shorter time here. This is older device. I think it was around 10 or 15. Yeah, we're still getting everything to work simultaneously. Okay. Okay, so now I told you how to do one qubit. If we want to do something complicated like quantum error correction, we have to look at a bunch of qubits. I'd rather not put one of these microwave chains for every qubit. So what we're trying to do here is, or what we've gotten to work, is frequency multiplexed readout, so that we can use one line, one D to A converter, one amp, one paramp, one thing, and measure more than one qubit at the same time. So what we do here is we see 3 qubits. They're connected to a different readout resonator, and these resonators are at different frequency, 6.36 and 6.46. And you can see it's different because this is shorter here, the different length here than here, and that this longer gives you a lower frequency. So what you do is you put in the 2 tones and send it through here. It interacts with this. You amplify it, and then you bring it out through a A to D converter and then a FPGA to do a digital mixer, so that each frequency you get an amplitude and phase, and then you can read the 2 states independently. So here's the result: 2-qubit multiplex readout. We have qubit A at one frequency, qubit B another frequency. It's in the 0-0 state, and we have a bunch of things, Gaussian, kind of a Gaussian packet here and here, and a few errors here. So it's here and here, the 0 state. I then put the qubits into 0-1. So now these reds are over here, not very many here, but this stays the same. Then do a 1-0, and all these are over here, and these are back in the 0 state. And then the black is 1-1, and it's here and here. And you see that all this stays well separated, and it's not like they're interacting much. So these are really like 2 separate measurements. We just frequency multiplex, we get out the data, and everything's okay. Okay, so that's measurement. And we're trying to do more multiplexing and make it faster, but it basically works. I now want to talk about qubit gate fidelity. This was talked about earlier by Ray LaFlamme on randomized benchmarking. We start in the 0 state, and then we do 0. You do 90-degree and 180-degree rotations, both in X and Y, to perform a series of what's essentially Clifford operations. And then we take the last operation, we choose it so that it would bring it back to 0. And if everything works properly, you would then get 100% fidelity. In reality, we have about 92 or 3 because of initialization and measurement errors. We're fixing that, but you're just worried about, as you add more of these operations, how does the sequence fidelity go down? And you see as you increase the number of gates, the fidelity goes down and down and down. And this is a really good randomized benchmarking because it's a very realistic test of a complex control sequence. You need good universal calibration so that this gate here is synthesized completely independently of all the other gates. You're not measuring tiny errors and the like. So we see this decay, but look here, the number of gates before it goes down by 0.1 or 0.2 of probability is hundreds of gates. There's 200 gates. At 300 gates, you've gone down about 0.15. So that's a lot of gates. And you work out what the fidelity of that is, and that's 99.93%. That's really good. Okay? And yeah, so we can get things working well. And this is basically, we think, more or less limited by the T1 of our device. So just to show you, this is not some hero device that we cooled down for 2 years to get it all tuned up and whatever, that this is more or less what we get when we get things are working right. Here's a device with 5 qubits, and I'm going to show 3 devices here. There's an Xmon here, here, and here. This is the one we saw, 99.92. This one, it's a little bit smaller gap in separation, so the T1's a little bit less, but that's 99.84, and this one is 99.86. Okay, so they're all, you know, it's all pretty good. This is just something we can get if things are working right. I do want to mention here that these T1s are 7, 12. This is better because it's a wider one. 20 microseconds. These are not our best qubits. They're also 20 nanosecond gates. So we make the gate twice as fast. We bring this up a factor of 3 or 4. We think 4 nines or close to 4 nines may be possible. We think that we might be able to get T1s above 100 microseconds. So we think we might be able to get really close to the ion traps. Okay? Thank you. And this is done, of course, with multiple qubits here. How do you know you can operate lots of qubits at the same time? Right? This is, I think Ray was mentioning that. A lot of these measurements are single qubit measurements. They're hero measurements. This is basically the same data where we just did 1 qubit at a time, more or less the same data you saw there. And then we ran 2 qubits simultaneously with randomized benchmarks, and then 3 qubits simultaneously with randomized benchmarks. And if you look at, say, the numbers down here, they're not too much different than here, more or less within the error bars. So we're going to say that there's really no effect of some kind of crosstalk when we're doing qubits simultaneously. And again, we have to look at this in more complicated situations, but we don't see a big problem in our system. I also want to mention a little bit about Z control. One of the things we're doing, it's super different than ion traps. In ion traps, you have these great clocks, and you know their frequency. And you would never want to change their frequency because then you might get some phase errors. What we're going to do here is something really different. We're going to be moving the qubit frequencies up and down so that if you have fixed coupling, when they're on resonance, they'll coupling. When they're off resonance, we'll turn off the coupling. Sounds crazy because when you're moving the frequency, you can introduce phase errors and then totally screw up your qubit. So are we crazy here? Okay. What this is an experiment is we take a qubit and then we do a 500 megahertz detuning on a 6 gigahertz qubit. That's a 10% change in frequency for 40 nanoseconds long. So it's 2 nanoseconds, 40, that's 20 2 pi qubit rotations. And we tune it up so it's exactly 20 to be the identity. Okay, now how do we know it's identity? We measure the qubit phase with the Ramsey fringe, and as the number of qubit Z gates goes from 1 to 10, we see a small systematic change of about 0.1 radian. So you say per 20 pi rotation, that's 0.01 radian. That's a 99.997% phase control per 20 2 pi rotations. So that's good. We know how to control it. And you can do randomized benchmarks, the X and Y, and now you're doing the 20 rotations here, and XY gates only, XY's interlaced. It's worse here because this is adding more time due to the detuning. And basically, this is twice larger because it's a twice longer sequence, and we're saying here this is no added decoherence due to the Z gate. So again, that's looking really, really good that we know how to do that. So for control Z, I'm almost done. What we're going to do is have this qubit capacitively coupled to a fixed resonator bus frequency. We bring this on resonance to swap the qubit excitation into here. Then swap that off so the excitation's here. Now what we do is we bring these frequencies together so that the 1-1 frequency of this composite system is on resonance with the 0-2, where there's two excitations here. And then the 2 pi rotation here gives us a minus sign for the control Z. And this is the kind of operation where we think we can get very good fidelity. And this is just showing you how we do that. We do a Ramsey fringe on one of the qubits, and then we either put a 0 into the control Z or 1. And if it's 0 or 1, with the Ramsey fringe, you'll see a different phase shift. So here's no X is a 0, X here is a 1. We see a pi phase shift corresponding control Z. And then you can do it the other way, and again, you see another pi shift. So this shows that the basic operation works. Then you can do quantum process tomography, where you put a variety of input states here and then measure them in a bunch of different axes, and then you extract out what the chi matrix is here. The open boxes here are what you expect for a perfect control Z, and the solid boxes here is what we get. And you see everything matches up really well. You get big weights where you expect that, and you work through the fidelity of this, and that's about 93%. So this is much worse than we want it to be. We want to be between 99% and ideally 3 nines. We think we know what's going on here. We're fixing it. Hopefully in a couple weeks to a month we'll have good fidelity CZ gates. But you know, it's definitely the hard thing to do, hard thing to prove, and we're working on that. But we know the basic operation is good. Okay, so I'm just going to conclude at this point. Are the Xmon transmons good enough for a quantum computer? Well, no, not yet, okay, but we're getting really close, and we're making a lot of progress towards what will be our next experiments, which will be error detection and trying to do fault tolerant computation in something that we can scale up. For the surface code architecture, we basically need about a 99% threshold, which is something we think we can get. It's also in an architecture and hardware that's basically totally compatible with integrated circuit fabrication. It may be hard in the future to get everything to work right, but we think it's possible with enough technology. We've been able to multiplex measurements so we can read a bunch of qubits, and the gates are coming along really well, and clearly we have to do that. And we really like this planar Xmon transmon. Being it's a 2D design, we think it should be good for IC scaling, but there's still lots of technology to work on, but it kind of makes sense. Now, where are we heading with this? We're trying to start up a scale-up project, and this is its long-term goal. We want to make hundreds to, say, 1,000 qubits in a surface code architecture. Right now, with the technology we have, let's say 20 qubits doesn't bother me at all. We could do that in a month if we wanted to do that. To get 1,000 qubits, we'll have to invent a bunch of stuff. I kind of see a path to do that. 1,000 qubits is interesting because that is enough qubits to make a square array and to show a full logical error rate of, I don't know, 10 to the minus 15, some ridiculously small error rate, that you could show that you could actually do fault-tolerant error correction. This is also big enough that you could make sub-arrays with holes in it that had, let's say, 10 to the minus 6 errors, but you could take those qubit holes and braid them around and do logical operations like C0 and X and other things to show that you can basically do the logical operations. And maybe single flux quantum control is possible, maybe not, we brute force it. But the idea is if you can show these two things, you've really then proven that the basic ideas between error correction and logical gates are correct, which I think is a big open question that we really want to work on. And then if this works and if you can figure out how to do the control, you can then, of course, make bigger systems. And that's when we'll ask for $1 billion to build the full computer, if we know how to do it. Maybe it'll cost more, I don't know. So, okay, thank you for attention.
Sorry, so don't you have a corollary there saying that you know, if you can do your 20 qubits in a month, then doesn't that apply SNP?
Okay, well, say that again.
Oh well, you know, you just said that you know how to get to 20 qubits in a few months or something. So doesn't that imply SNP? Some Nature publications.
Yes, absolutely. There are Nature publications along the way that are very nice, but you have to have a big group all working together, solving the technology problems, and then everyone has to share the publication.
Right. So,
but there are exciting experiments to do along the way. Yeah. But you have to convince everyone to work on the technology.
Right. So yeah, but my serious point was, you know, I don't know about you, but 20 qubits would be quite exciting, wouldn't it?
I agree. Okay. But it's really, I want to emphasize how hard all the students and postdocs are working to get all the technology together. But, you know, like I say, we think it's not going to be too insane to actually scale up to, you know, 20 qubits. Now, to scale up to hundreds or thousands, that's going to look like a high energy physics experiment. That's a whole nother level. But yeah, we can do this. We're just not going to maximize, but some, yes. Some is okay at this point, yes. Yes, Ray.
You must have something headed up your sleeve. If you're thinking that in a month you can do 20 qubit, if your 2 qubit gate is 7%,
okay,
and you do
so
20 of them.
The first thing we have to do is make our 99 or 99.9%. Okay, the 99 I'm pretty sure we can do because we've kind of already done it. I just want to do it in a clean way, and then it may take more than a month. Maybe, you know, in a month we could do it. It's probably going to hopefully take us 3, 4, 5 months to get everything figured out to do the more complicated experiment. But I'm just saying that all the kind of the technology and infrastructure is kind of there, and people just have to work weekends to get it, you know, to do that. You know what I mean? Yeah. It's like at some point it's like
a long month.
But we'll see. I mean, things can go wrong. Okay, it's looking good, but you know, I want to demonstrate the results like we did with the single qubit. The single qubit results are like 1 or 1.5 months old, and basically the first time they tried it carefully, it worked fantastically. So we're very optimistic at this point.
Related to this on error, an error model, when you look at your single qubit errors, can you see that it is Markovian? Can you see?
Yes. So what we can do is you can interleave the Clifford gates with like an X gate or a Y gate or a Z gate. And when you do that, I have the slide, but it's just not up here. You see that there's no real, not one of them is not bigger than the other ones. So there's no obvious problem there.
But what I have in mind is if you look at a log plot, is it a straight line? If you take a plot on the error as a function of number of gates,
well, it
and if
goes
it's Markovian,
down and then flattens out.
If you have a number of gates, but take the log of it, so it should be an exponential. If it's Markovian, it's going to be straight. And if it is not Markovian, then it starts to fluctuate.
Let's talk. Yeah, let's talk about that. There's something here.
Same thing for 2 qubits. Do you look at correlation between errors? Can you?
No, okay. We haven't. We're working to improve the gate before we look at it too carefully. we should talk. I think there's something you could help us understand. But we have looked at some things more than this. But let's talk.
Okay, just maybe one more question.
As far as I understand, you can now do a very long, like 20 qubit long chain. But what about 2D structures? Because
yes,
you will need to change your coupling scheme for that.
Yeah, and what you saw here was kind of a linear chain, and we have an idea of how to do like a real 2D structure. And the basic idea is you wire up the qubits 2D in your really good qubit process, and then you use some other process to do kind of in the third dimension to bring out the control wires. And that's going to require the big technology investment.
So that will cost you in fidelity and coherence time, right?
We think what we understand is if we bring the wires out in the third dimension, we should be able to do that cleanly from what we understand. But we have to show that. But we have some ideas, and I think that looks pretty good. But this is going to be some real development.
Okay, so let's thank John again.